All right, so I hope now we have been now introduced to measurement as a science, and we now understand to some extent about the importance of measurements and instrumentation. And also, we have now seen some of the applications of measurements and the instruments. But in the previous slide, we have seen the two fundamental methods of measurement, which involves direct comparison and indirect comparison. And we have seen that traditionally we have been using direct comparison, or we do use direct comparisons, in our domestic, you can say, applications. But indirect comparisons are something that are used mostly in the industries and for very important applications because of their accuracy and other features. Now coming to the standards and units, because this is also very important to know in the introduction, that we have seen that we do compare with standards. So what are the standards actually for measurements, and what are the units? Units are the basic part of measurements. For example, if you're measuring length, so what is the basic length that we want to define, where we can actually multiply or we can have subdivisions of this. And standard obviously is the standard for that length. How do we define that unit? So we need to have an established some clear rule about that. What actually defines meter, what is a meter, or what is a what is the second. All those physical units actually need to be defined as they need to have a standard. So it all started actually with the barter trade, as we have already discussed, that where we actually would exchange the goods, and we wanted to quantify the relative the value of the goods. For example, if somebody would sell some clothes for milk, so how do we sell it? How do we relatively sell it? Do we sell more clothes or do we sell less clothes? What is the appropriate actually units with which we can actually quantify different objects that we are actually buying and selling? So these things actually were conceived or established from that time only, where the quantity being exchanged was actually we had to quantify them properly, or we can see we had to establish clear rules about the relative values of the commodities. And obviously, as we have seen already, for length, for example, we used to have human torso, with which actually we have got these units of hand, foot, cubit. And obviously this was adequate for the barter system, where it wasn't really that important to have a small error in these things. Obviously, we have seen that they were generally imprecise and varying as per different persons, and hence they were inappropriate for actually the industrial use, where we talk about highly accurate, measurements, and obviously their impact on the large scale production. So now, the first improvements that were made actually in these standards and units was the definition of the unit length. So what we call in literature this as the first improved measurement unit, and actually it was the unit of length, which was defined as meter, and it was given the definition that it's equal to 10 raised to the power -7 times the polar quadrant of the Earth. So obviously it's from the equator to the North Pole, the along the greater circle, we define it that way. And it was in the early 19th century that a platinum bar was used, of this much length, was used as a standard, I can say, metal for actually keeping this as the standard for the meter. And similarly, in 1889, a superior quality platinum iridium alloy was used of this much length, that is 10 to the power -7 length, -7 the polar quadrant of the Earth, was used as the basic standard length, you can say length standard that was used, so that we could quantify or we could compare any other standard quantity with these basic standards. So the technological research now enabled further improvements in defining these standards. We were able to measure various other parameters or various other things in the using physics, basic physics, and all this chemistry. So we redefined in 1960 the meter was redefined as the wavelength 1.65 × 10⁶ wavelengths of the radiation from krypton 86 in vacuum. This is actually an inert element, and this was used to define the meter. But obviously, as things improved, so in 1983, the meter was again redefined as the length of path traveled by light in an interval of 1 by 2997 and 2458 seconds, which is almost, you can see the speed of light that we have seen. So we could measure the speed of light, and accordingly we could define the meter as this. Now this is obviously something that the meter definition still holds. And similarly, the standard units for other quantities like time, where we have seconds, and obviously for other the other quantities was developed and improved over time. We have some basic definitions of or basic units that were also used, because if we say meter, so why don't we say millimeter, why don't we say kilometers as the standard? So obviously for that, the basic no this was to be established, what is to be taken as the basic unit. So like meter is defined as the basic unit. So, and similarly we have kilometer, or we have for time, we have seconds. But obviously we could see that there were developments in different countries during this 19th century, where we had developments in the European and the American side, where we had developments taking parallel, developments taken in parallel, and obviously everybody developing their own standards. So for example, in British, or in the United Kingdom, we have seen there were something called imperial units, or in the US we had some other units. So obviously when you're comparing, or when there's a trade between the countries and the global trade, we need to obviously have some basic standard units throughout the world. So that's what we call SI units, or systems international, or you can see international system of units was developed. It was established that we should use a very common unit so that we can trade actually throughout the world. Obviously, so this is also called as internationally agreed set of standard units. It was easy to convert, you can say, as a metric system. So each standard unit has a very simple relation to its subunits. For example, meter to millimeter is just 10 to the power minus 3. Similarly, meter to centimeter is very simple, or centimeter to millimeter is also simple, or meter to kilometer is 10 to the power of 3 meters is equal to 1 kilometer. So this was very easy as SI units. But obviously, as an example, this is meter, kilogram, etc. But as an example, we have seen that there was also something called imperial system that was being practiced in US and UK, where we had cumbersome multiplication factors relating fundamental units. It was very difficult. So we have basic definitions like yards, feet, inch, pounds, etc. So we had a cumbersome multiplication factors relating the fundamental units. Say for example, the conversion between feet and inches. So obviously, if you are aware, 12 inches is equal to 1 feet. So the conversion factor is actually 12. Or you can say, if you want to say how many inches, so 10 inches, how many does it actually make in feet? So you have to say 1 by 12 into 10. So this was a cumbersome multiplication factor actually that was there. So similarly, from yards to feet, you have again some cumbersome multiplication factors. So this was in a way kind of complicated or cumbersome, or you can say this was discouraged. But obviously this is still being used in the UK as the imperial system. But the World Trade or organization or all such are actually recommending. But you have some various agencies actually that recommend following a very standard unit, that is SI units. Now these are some of the other definitions. For example, the length we have already defined. This is something that is defined at present. So mass, for mass we have kilogram. This is the mass of a platinum iridium cylinder kept in the International Bureau of Weights and Standards in Paris. So these standard these metals, or you can say these alloys, are actually kept in those conditions where their properties really don't change much. And so it's more of a a very standard place in terms of temperature, so that temperature doesn't have an effect on its expansion and other things. So it remains it remains of the same weight that we want it to be, because that is acting as a standard. Similarly, second is defined as 9.192631770 into 10 to the power minus 10 to the power 9 cycles of radiation from vaporized cesium-133, which is having an accuracy of 1 in 10 to the power 12 or 1 second in 36,000 years. So this is such a accurate, actually standard. Temperature we use Kelvin. The definitions are here. For current we use obviously ampere. So these are all some things that we already know. For luminescence intensity we have candela, and for matter we have mole, which is defined as the number of atoms in a 0.012 kilogram mass of carbon-12. So now these are the fundamental units. So for length we have meter. So we don't use millimeter as the fundamental unit. We have meter as the fundamental unit. So millimeter would be the derived unit, or you can say subunit. And we could have kilometers also, which can be also it's a derived unit, or you can say it could be again it's not a standard unit. So you should remember this thing. For mass we have kilograms. We don't have grams as the standard unit. Kilogram acts as the standard unit, and you should be very careful about these symbols. This is very, very important. For meter we don't use capital M, we use small m. For kilogram we don't use capital K, we use small k, small g. This is also very important to remember. For seconds we use small s. For current we use capital A. For temperature we use capital K, and similarly others. So for time we don't have millisecond as the standard, we have seconds as the standard. So these are all SI units. You can say standards, international standards are the basic units of these physical quantities. Similarly, we have something called as derived units, which are actually derived. For example, area is actually derived from meter only, so we can have square meter. So meter square is actually the standard unit. It's not millimeter square. All right. Similarly, we have for volume, we have cubic meter, which is the standard unit. We don't have cubic centimeters as the standard unit. Similarly, for velocity, we have meters per second as the standard unit, not millimeters per second or millimeters per hour or kilometers per hour, but meters per second is taken as the standard unit. Similarly, for acceleration, meter per second square, and similarly for various other things. For density, we have kilograms per meter cube. We are aware. For force, we have Newton. For power, we have watts, capital W. Be careful about it. For work, heat, and energy, we have joules, which is capital J. And similarly, for electric resistance, we have ohms. For electric inductance, we have Henry, capital H. Electric conductance, we have Siemens. So all these are the symbols for these quantities, and these are all the standard units for all these physical quantities. So it's very clear now. Symbols are very important in measurements. The standard units is very important. You need to measure actually these things, and sometimes you could have even the formula for these. Obviously, these are the derivation formulas. So Newton is nothing but mass into acceleration. So this is how it forms, and this is actually equal to Newtons. All right. So we have seen that there are some standard definitions, and the standard units are defined, and then we have symbols defined, and then also we have standard definitions for length, mass, time, all these physical quantities. We have some standard definitions. So obviously this is how they are actually defined. So this is very important for obviously trade, and obviously in the industries where we are actually doing a lot of production or manufacturing activities. So we obviously need to measure, we need to design, we need to produce, and they must be of these standards of which is actually more common to the whole world. So that's why we have international standard unit or SI units. Thank you.